So let's take a look at some quantifiers. And the two quantifiers that we're going to look at is the universal quantifier, for all, and the existential quantifier, there exists. So the way that we remember the universal quantifier versus the existential quantifier, which of these two symbols is which, you'll note that for all, our universal quantifier is an upside down A. So we take the letter A and we spin it upside down on its head. And that stands for all. The existential quantifier, there exists, there's an E in it. And you'll note that we take an E and we reverse it. And you might think, well, why didn't we turn them both upside down? Why didn't we flip them both side to side? Take a close look. If I just reversed the A, I'd still get an A. And if I flipped an E upside down, I would get back to the letter E. So this wouldn't work. And so we'll settle on an upside down A and a backwards E. Let's first take a look at the universal quantifier, for all. And we have a predicate P over some universe U. And if we add this quantifier in front of it, it reads, for all x in U, P of x. What this becomes a proposition, and it's true if for every possible object in the universe, P of x is true. It must be true for every single item in the universe. Our other quantifier, there exists, our existential quantifier, also turns P of x into a proposition. But this time it reads, there exists an x in the universe, U, such that P of x. So this is true if there's at least one item in the universe such that P of x is true. So now we only have to find one to make that be true. So let's consider the following and think about what they mean. Okay, first of all, are either of the following true? For all x in the universe, z greater than or equal to 2 is prime. What that's saying is all integers greater than or equal to 2 are prime. And part B is saying there exists an integer greater than or equal to 2 that is prime. So are the following true? Well, the first one we know is false because 4 is not prime. So the first one is false. But part B says there exists an integer greater than or equal to 2 that is prime. And this we know is true. We can list several. We only need to list one, but we know that 2 is prime, 3 is prime, 5 is prime, 7 is prime, 11, and so on. So the first is false, the second is true. Let's consider the following two statements. For all x in z greater than 3, sum of 2 primes of x. What is that saying? That's saying all integers greater than 3 can be represented as the sum of 2 primes. And how about part D? This says there exists an x in z greater than 3 such that sum of primes of x is true. And this can be written as there exists an integer greater than 3 that can be written as the sum of 2 primes. And these are very different statements. So can I find an integer that can be written as the sum of 2 primes? Of course I can, because I can use the integer 5, which we saw as our previous example. 5 is equal to 3 plus 2. Both 3 and 2 are prime. 5 is greater than 3, and so there does exist an integer greater than 3 that can be written as the sum of 2 primes. However, for part C, so while this is true, because 5 is equal to 3 plus 2. This is false because we know that we can't do this for 17. 17 does not work. So in this case, there's an example for which this fails. And so it doesn't apply to all x greater than 3. So let's talk about some intuition for this. What is the big idea? Let's think about this in terms of loops. How do we know if we meet this criteria or we don't? Well, for the universal quantifier, what we need is everything to pass this test. We want for every x in the universe, p of x to be true for this to hold. So this is, in order to do this, we're going to have to loop through all possible x. And if we find any that fail, if any of them fail, the whole thing is false. So we look through them all. If any fail, the proposition fails. On the other hand, if we look at the existential quantifier, there exists an x in U such that q of x is true. Here we're going to loop again through all the possibilities. And if we find any that match the criteria, the whole thing is true. So we loop until we find something that's true. If we do, it's true. If we don't find any, then it's false. We can also think of these in terms of conjunction and disjunction or. So the universal quantifier, if you want to think of it applying to a set U, x1 to xn, so if we think about this in terms of conjunction, what we're actually saying is for all x, p of x, to be true, we need every single element in the set to have this condition hold. We need each of them to be true for this to be true, because it's like p of x1 and p of x2 and p of x3 and all the way out to p of xn. So for all is true if all of them meet the criteria, and false if any of them do not have a true truth value. With the existential quantifier, there exists an x in U such that q of x is true. Instead of a conjunction, we look at disjunction. And so this acts exactly like q of x1 or q of x2 or ... q of xn. And so we need only one of them to meet it for this to be true. Just as in a disjunction, we only need one of them to be true. The same is true with there exists for the existential quantifier. It's important to note that for all and there exists, they bind tighter than logical connectives. So if you see something written without any parentheses and it reads like for all x in U, p of x is true, implies that there exists a y in U, p of y, there's brackets that you can't see holding these pieces together. So they bind tighter than the logical connectives. And while we don't include those parentheses when they're not needed, they're there in theory.